All right, let's dive into a problem that has probably frustrated anyone who's ever worked in ceramics. We're talking about understanding what's really inside your raw materials. Because as we're about to find out, a simple chemical formula, well, it barely scratches the surface of what makes or breaks your final product.
So picture this. Your main supplier for, say, a feldspar can't deliver. You find a new supplier, and the data sheet looks amazing. The oxide percentages are a perfect match for your old stuff. So you feel confident, you run a full production batch, and it's a total disaster. What on earth went wrong?
And right here, this is the heart of the mystery. On paper, feldspar A and feldspar B are twins. The data from your standard chemical analysis, the XRF, is identical. But look at the results. One gives you a perfect product, batch after batch. The other one leads to cracking, warping, and a massive headache. And listen, this isn't just bad luck. It points to a fundamental misunderstanding of our materials. To solve it, we really need to go back to basics.
Okay, so every traditional ceramic body, whether you're making tiles or tableware, is basically built with a team of 3 key players. Once you understand their roles, you're on your way to figuring out why things go so wrong.
First up, you've got your plastics. These are your clays, like kaolin and ball clay. The best way to think of them is as the binder, or the glue. Their superfine particles are what give the clay its workability, its plasticity. This is what lets you shape it, and crucially, have it hold that shape before it ever sees a kiln.
Next up, you have the skeleton. This is usually something like quartz or flint. Think of this as the literal framework of the body, like the rebar in concrete. It doesn't do a whole lot at low temperatures, but it provides the structure, it controls shrinkage when drying and firing, and it stops the whole piece from slumping into a puddle. And finally, we have the fluxes, like those feldspars we talked about. These are the melters. Their whole job is to lower the melting point of the entire system. During firing, they form this gooey, viscous liquid that flows in between all the other particles, pulling them together and creating a dense, strong, glassy final product. That's vitrification.
Okay, so if we know all these roles, why are we still running into problems? It's because the true identity of these materials is kind of hidden. It goes way deeper than just a simple list of chemical oxides.
Now, your chemical analysis, that XRF report, is absolutely crucial. Don't get me wrong, it tells you what elements are in there, how much silica, how much alumina, and so on. But it completely leaves out a piece of the puzzle that is just as important.
And that is how those elements are actually arranged. I mean, look at this. The chemical list on one side looks so simple, right? But the real identity of a material includes its mineral form, its particle size, its shape, all these physical things that completely control how it's going to behave in the real world in your factory.
This is the perfect analogy for it. Seriously, you'd never swap sugar for molasses in a baking recipe and expect the same cookie, would you? Of course not. Their form, their impurities, their moisture content, it all changes the outcome. It is the exact same principle with our ceramic materials. So this brings us to a key concept, mineralogy. This is the material's crystalline identity. It's not just about having silicon and oxygen. It's about whether those atoms are structured as quartz or as part of a feldspar crystal. Because those different structures have totally different melting points, and they behave in completely different ways when you heat them up. And then there's the physical form, and specifically particle size distribution, or PSD. This is huge. A finer powder is going to melt faster and shrink a lot more than a coarser one, even if they have the exact same chemistry. It affects everything from how your liquid slip flows to how the particles pack together, which directly impacts the final strength of your product.
So how do we stop guessing? Let's build a practical toolkit. How do we actually measure these hidden properties and unmask our ingredients so we can prevent those expensive production disasters?
Here it is. This is your essential diagnostic toolkit. XRF for chemistry, that's your starting point. But you absolutely need XRD, X-ray diffraction, to figure out the mineral phases. You need a way to measure particle size distribution. You also need to check the loss on ignition. That tells you what burns away, and you have to analyze those pesky trace elements like iron and titanium that can completely change your fired color.
And this chart, wow, this illustrates the whole point perfectly. Just look at the data for these different commercial clays. They might all be sold as kaolin or ball clay, but check out the differences. The amount of actual kaolinite mineral, the quartz and mica impurities, and especially that fine particle fraction, the percent of particles under 2 microns. It's all over the map. This right here is why you can't just sub one ball clay for another and cross your fingers.
So let's get down to the practical payoff. How do we actually use this knowledge in the real world?
We're going to build a simple, no-nonsense checklist for any time you have to think about a new material or switch suppliers. This is how you protect yourself.
All right, here's your 5-step checklist. 1. Do a quick lab firing test, just a small sample to see how it melts and shrinks. 2. Check the slip rheology. Does it make your slip thicker or thinner? That matters. 3. Look for color shifts. Compare the fired colors side by side. 4. Verify the thermal expansion. You don't want a mismatch that causes your glazes to craze or shiver. And 5, this is the most important. Before you go big, run a small, controlled experiment. Isolate that new material in one small batch so you can confirm its true impact without risking everything.
So, it all boils down to this one question. Looking at that chemical analysis tells you what is in your recipe. But to truly control your process and make a consistent, reliable product, you've got to go deeper. You have to understand the whole story. You have to know who your ingredients truly are.